Hello, in this video we study triple integrals in order coordinates. Before we move to detail, let me remind you about polar coordinates. If you have some point in the plane, right here, x, y, you may find the angle between the vector with the x-axis, let's say theta, and of course you may find the length of this vector, which is square root of x squared plus y squared, right? We denote by r. So from here we may transfer to polar coordinates as r and theta. Make sense? And the relation between them is x equal to r cosine of theta and y equal to r sine theta. That is the vector in the plane. So what happens if you consider points in the space? That means we have to involve the z coordinate, right? Look at this. Suppose that you have some vector x, y, z, or a point in the space, right? So we already know x is equal to r cosine theta, y equal to r sine theta, where theta is the angle between, right, the vector right here in the xy plane and the x-axis. Okay, that is polar coordinate I just mentioned. So if we give right z equal to z, then we have the following triple: r, theta, and z. And this is called cylindrical coordinates. Make sense? Sometimes when you need to integrate a function of three variables, like we learned in the previous video, we know if you want to find the first and the second moments of some solid region, you have to use triple integrals, right? And sometimes the region, the solid region, looks like spheres, right? So, in that situation, maybe we need to work with spherical coordinate. How to see that? Basically, you have x equal to r cosine of theta, y equal to r sine of theta, okay? Now, r is right here. Makes sense? Where this point is, just orthogonal projection of this vector on the xy plane. Let's denote by rho the length of this vector right here. Okay? So the relation between rho and r is that r is equal to rho sine of phi. Make sense? Because here you have right triangle. Okay? So, on this triangle, you may find that actually r is equal to rho sine of phi, where phi is the angle between, that vector and the z-axis. So you just translate everything to rho, phi, and theta. R is rho sine theta. How about z? Z is right here, right? So z is rho cosine theta. And the triple rho, theta, phi are called spherical coordinates of this point. So basically in this picture you see three different coordinate systems. Make sense? Rectangular, cylindrical, and spherical. And today we'll consider some examples when we need to use cylindrical, when we need to use spherical, and when we need to use rectangular. In the following example, we have some sphere, x squared plus y squared plus z squared equal to 4. So this sphere is centered at the origin and radius equal to 2. They ask us to find the volume of the solid region Q cut from the sphere by the cylinder, r equal to sine of phi, as shown in the picture right here. Okay, so what is r equal to 2 sine of phi? Look at this. If you draw the xy plane, right, you have 2 times sine of 5. What is that? That is, 2 right here. And the circle center at 1, radius equal to 1. So that is your r equal to 2 sine of theta. Okay, and then you consider some, cylinder, which is free with respect to the z, right? So you have that cylinder right here. You see, that cylinder. And imagine that, the cylinder will intersect with the sphere by some curves, right? And that makes some solid region. This is in here. So we need to find the volume of this solid region. Firstly, we need to write the integral of the volume. And we know that the volume is equal to triple integral over Q, where Q is our solid region, dV, right? So we need to rewrite this integral in terms of iterated. Let's do that first, and then we move from rectangular coordinates to cylinder coordinates. So you may choose dz, dy, dx. That's what we used to do, right? So I need to find integration limits for the x, for the y, and for the z. Make sense? All right, look at this. How to find that? If you write in this order, so probably you need to fix the point x and y first, right? On the xy plane. So if you fix some point on the xy plane, right here, you need to find the interval of z. In order to do that, we draw a vertical line, right? That vertical line will intersect with our surface at 2 points, right? So let's say this is z1, this is z2. We need to find z1 and z2. How to find that? We can find that in the equation of the sphere, right? Because, that straight line intersects with the sphere at 2 points. So I need to solve for z. From the equation of the sphere, I have z squared equal to 4 minus x squared minus y squared. And from here, I get z equal to plus minus square root of 4 minus x squared minus y squared. The interval is from negative square root of 4 minus x squared minus y squared, right, to square root of 4 minus x squared minus y squared. Make sense? And then we move to the y. In order to see the y, we need to look at this picture. Make sense? But it's for this picture, that is the circle center at 1, right? Radius equal to 1. So you can write the equation of the circle. That is x squared plus y minus 1 squared equal to 1. You see that? And in order to find the y distance, right, I need to fix x, right? And I solve this equation for the y. Make sense? So each time when I fix x, I will draw a vertical line right here. So I need to find this point and this point. But it's pretty easy. I can solve this equation for the y. I get y minus 1 squared equal to 1 minus x squared, and y minus 1 equal to plus minus 1 minus x squared, right? And from here I get y equal to 1 plus minus square root of 1 minus x squared. So you have the interval of y when you fix x. You see? So I have to plug y1 and y2 in here, where y1 is 1 minus square root of 1 minus square root of 2 x squared, and y2 is 1 plus square root of 1 minus x squared. Okay, and after that we need to find the integration limits with respect to the x, and we see from here x go from where to where? From -1 to 1. And our job is to evaluate this integral. But of course, look at this. You have complicated integration limits, right? You have complicated y1 and y2. So that makes our life maybe more complicated. Make sense? We may choose the way of polar coordinates, but in three-dimensional case, so which is called cylindrical, right? We just translate x and y into r and theta. Make sense? All right, so let's do that. If I use x equal to r cosine of theta, y equal to r cosine of theta, and z is the same, right? You know, we just add z to that, right? From here we get x squared plus y squared equal to r squared. Make sense? And of course, we also have, I'm sorry here, I mix, this should be sine of theta. From here, I also have tangent of theta is equal to y over x. And those identities have us to go from rectangular to cylindrical, okay? Let's rewrite our integral in the cylindrical coordinates, z, r, and theta. So we need to determine integration limits, right? First, let's find the integration limit with respect to the z. So look at this integral. Z will go from negative square root of 4 minus x squared minus y squared to square root of 4 minus x squared minus y squared. But what is this? This is nothing but 4 minus r squared, right? Because of this, right? So I have, this is negative square root of 4 minus r squared less than or equal to z less than or equal to square root of 4 minus r squared. You know, we need to translate x and y into r and theta, right? Don't forget that. So we have the interval for z. Next, we need to determine the interval of r, right? They give us some circle, right? Center at 1, radius equal to 1. And this circle is r equal to 2 sine of theta. So from here you can see actually r will go from where to where? Go from 0 to 2 sine of theta. Because you know our point cannot go out of the circle, right? Makes sense? So we have the interval for r. And then we need to find the interval of theta. What's that? If you are in this, means, you know, in the x-axis, theta is 0. And if you are in this direction, so you have pi right here. And if you pick any point, right, inside the circle, the theta is in between 0 and pi. So that is the interval of theta. All right? I think we have all information. Now we need to rewrite the integral. I choose the order d, z, dr, d theta. For r, I have negative square root of 4 minus r squared. In here, 4 minus r squared, that is for z. And for r, I have 0 to 2 sine of theta. And for theta, I have 0 to pi. And don't forget, we have r in this case. Because when you rewrite this, right, the y and dx in terms of dr, d theta, so you need to change the coordinates, right? And that's what we learned from double integrals. We need to add r in this case. Make sense? So the last step is just evaluate this integral. This equal to 0 to pi, 0 to 2 sine of theta. And since r is constant with respect to the z, so you have just r, z evaluated from negative 4 minus r squared, square root of 4 minus r squared in here, okay, dr d theta. And you just plug those numbers into the position of z. 0 is 2 sine of theta, r. So you have square root of 4 minus r squared minus negative square root of 4 minus r squared dr d theta. And what you get in here is 2 4 minus r squared, right? And we have r in here, dr d theta from 0 to 2 sine of theta, from 0 to 2 pi. All right, so, you know, in this situation, we cannot rewrite this as product of two integrals. So we did that several times in previous videos, right? But in those examples, you know, all integration limits and the function here can be separated. But in this case, given that the function depends on only r, right? But the integration limit depends on theta. So there's no way to rewrite as product, okay? So we have to integrate the inside function. But you can see 2r in here and 4 minus r squared. So I will put u equal to 4 minus r squared. I have du equal to negative 2r dr, right? Or I see dr equal to du over negative 2. Makes sense? Now, I can change the integration limits right away. I may do like when r equal to 0, u equal to 4. And when r equal to 2 sine of theta, u equal to 4 minus 4 sine square of theta, right? Which is 4 1 minus sine square, and that is just 4 cosine square of theta. Okay, now let's rewrite the inside integral. Okay, that is equal to integral from 0 to pi. Nothing changed with that. In here I have 4 to 4 cosine square theta. R dr, 2r dr is just negative du, right? So I have negative in here and then square root of u du d theta. Okay, so I have negative 0 to pi, that is u 3/2 over 3/2 evaluate from 4 to 4 cosine square theta. And I have d theta right here. Okay, now I just plug, you know, these two values into the function. I get negative 2/3, because I just bring this part out. Okay, integral from 0 to pi, and we have 4 cosine square theta to 3/2 minus 4 to 3/2 d theta. This is equal to negative 2/3 from 0 to pi, and here we have 8 absolute of cosine theta minus 8 d theta. What do we have absolute in here? Look at this. We have 4 cosine square theta, square root, right? And then apply the cube. You have 2 absolute of cosine theta, right? And cube. Yeah, we have cube right here. Makes sense? So we need to open this, you know, absolute. But this is very special case, right? You have cosine here from 0 to pi, right? And this function is, you know, symmetric with respect to the y-axis. Makes sense? So integral from 0 to pi over 2 should be equal to integral from pi over 2 to pi. That means I can rewrite this integral as negative 4 over 3, means 2 times, right? Here from 0 to pi over 2. And when theta from pi over 2 cosine is positive. I have 8 cosine cubed theta minus 8 d theta. Make sense? Alright, so we have that is negative 4 thirds integral from 0 to pi over 2 8 cosine cubed theta d theta and plus 32 over 3 0 to pi over 2 d theta. We have negative 8 right here with negative 4 thirds, right? So you have plus 32 over 3. Okay, so this is nothing but pi over 2 and then multiply with 32 over 3. So this gives you 16 pi over 3. So we need to evaluate the first integral. Okay, let's take 8 out. So we have negative 32 over 3 integral from 0 to pi over 2 cosine cubed theta d theta. We learn such integrals in calculus 2. So, in this situation, we have 3 right here. So you can break it as 0 to pi over 2 cosine square theta times sine times cosine theta d theta, right? And what is cosine square? That is 1 minus sine square theta cosine theta d theta. And we need to do substitution. I put u equal to sine theta. Okay, and I have du equal to cosine of theta d theta. You see, we have this combination right here. And if you want, you can change the integration limit when theta equal to 0. U is just 0. When theta is pi over 2, u is sine of pi over 2 equal to 1. So this integral is equal to integral from 0 to 1 minus u square du. And this already very easy one. You have u minus u cubed over 3 evaluated from 0 to 1, which is 1 minus 1/3 is 2/3. Okay, so you bring this 2/3 to this, right? Overall, you have to multiply this guy with 2/3. Okay, and this equal to negative 64 over 9. Right? So you have this number and this number. Let's add them together. You have plus 16 pi over 3. So overall you have 1 over 9, 48 pi minus 64. And that is the final answer. Make sense? So what did we learn in this example? Why do we need to go from rectangular to cylindrical coordinates? Because our solid region was obtained from a cylinder. Look at this. You see? This is, the intersection between the sphere and the cylinder. So it is easier to use cylindrical coordinates. Alright? Now let's talk about triple integrals in spherical coordinates. Remember that we have x equal to rho sine phi cosine theta, y equal to rho sine phi sine theta, and z equal to rho cosine phi, where rho is the distance from the point xyz to the origin. And from these relationships, we have the following identity. Sum of squares of x, y, and z equal to rho square. That is easy to see, right? And if you divide y by the x, you get tangent of theta. And so if you want to find the angle phi, you solve this equation, the third equation for cosine phi. You get z divided by rho, right? But rho square is what? This x squared plus y squared plus z squared. So cosine phi is just z over square root of sum of squares. This is how we can go from rectangular to spherical and go from spherical to rectangular coordinates. Okay, so I will write the formula of triple integrals in spherical coordinates right away. Okay, if you have some triple integral over solid region Q, f of x, y, and z dv, then you can rewrite it in spherical coordinates. So you have f of rho psi of phi cosine of theta. Instead of x and y and z, you just plug, their formulas, right? So you have the next one is rho cosine of, psi of phi and psi of theta. The last one is rho cosine of phi, right? That is about the function f. And inside, you still need to multiply with rho square psi of phi d rho d phi and d theta. Look at this. It looks big, right? And of course, you need to find, integration limits in here. It really depends on how your solid region looks like. Okay, so I just write, in general, theta 1, theta 2, phi 1, phi 2, and rho 1, rho 2. So let's accept this formula without explanation. All right. Now let's consider some problem with spherical coordinates. We have some cone x squared plus y squared equal to z squared, and sphere center at the origin, radius equal to 3. Okay, and ask us to find the volume of the solid region Q bounded by the upper nab of the cone and above the sphere. So here it is. And this is our solid region. Okay, let's write the integral of the volume. That is triple integral again over Q. And let's say dv. That is very general, right? And now we need to decide rectangular coordinates are good, or cylindrical coordinates are good, or spherical coordinates are good. Okay, let's write them down. If I want to use rectangular coordinate, so I need to find projection of this part on the xy plane. Okay, that means I have to find intersection, right here and here. Makes sense? That should be the circle, right? So if you write intersection, you have x squared plus y squared plus z squared equal to 9, and z squared equal to x squared plus y squared. Because all points on this circle should satisfy the equation of pole surfaces, right? From here you can see actually you have 2z squared equal to 9, right? And z equal to plus minus 3 over square root of 2. Is it correct? But we consider the part above the xy plane. So I pick z equal to 3 over square root of 2, right? And then I plug this into this equation. I have the equation of the circle. 9 over 2. This is the circle on the xy plane. Right? So If you just find projection right here, so you have that circle. Make sense? All right, that is good. Now, let's rewrite this integral in the rectangular coordinates. And then we will pick the suitable one. Make sense? So I want to rewrite in terms of iterated integral of dz, dy, and dx, right? And if you fix some point x and y right here, right, you can find the interval of z. But in order to do that, you need to plot the vertical line, right? That vertical line will intersect with the cone at some point and with the sphere at another point. So that is the interval of your z. Make sense? So basically, that goes from the equation of the cone to the equation of the sphere. Here should be square root of x squared plus y squared. And here I have square root of 9 minus x squared minus y squared. Why? Why? Because you see this from where? From the equation of the cone, right? And all points are above the xy plane, so they are positive. And this comes from the equation of the sphere. Make sense? All right, so we are done with the z. Now let's move to the y. In order to find the integration limit with respect to the y, we need to draw the circle. So let's say you have the circle right here, right? Center at the origin, radius equal to 3 over square root of 2. You fix x, you draw some vertical line, right? And you need to find the interval of y right here. So basically, I need to solve this equation with respect to the y to find the interval of y. So I have y squared equal to 9 over 2 minus x squared, and y equal to plus minus 9 over 2 minus x squared. And I just copy these two numbers in here. We get negative square root of 9 over 2 minus x squared, square root of 9 over 2 minus x squared, but with plus in here, okay? And x goes from where to where? It goes from negative 3 over square root of 2 to 3 over square root of 2. You see, it looks very complicated one, right? And from the previous example, we know if you have x squared minus y squared in here, right? Probably you can use cylindrical coordinates. Make sense? All right, let's rewrite the volume integral in terms of cylindrical coordinates. All right, so we start from this integral, right? We have x squared plus y squared equal to r squared. Okay, and we have x equal to r cosine of theta. And we see we need to find the region of r and theta, right? So this is our circle xy. You go, and this circle is just, theta between 0 and 2 pi. R is in between 0 and 3 over square root of 2. Then the integral becomes, if you write in dz, dr, d theta, right? So for the z, you have from square root of r squared to square root of 9 minus r squared. For the r, you get 0 to 3 over square root of 2. For the last one, you get 0 to 2 pi. This is the integral in terms of cylindrical coordinates. I think we forgot r in here, right? Don't forget this. All right. Let's find this integral. And then at the end, we will solve using spherical coordinates. And you can see actually in this situation, spherical coordinates work really well, right? All right, so I need to integrate the inside function in here. So this integral is nothing but r times square root of 9 minus r squared minus r, right? And this is r square root of 9 minus r squared minus r squared. We plug this into our integral. We get integral from 0 to 3 over square root of 2. Here dr d theta, okay, from 0 to 2 pi. Again, the inside function does not depend on theta, right? So we can rewrite this as product of two integrals from 0 to 2 pi d theta times 0 to 3 square root of 2 r square root of 9 minus r squared minus r squared dr. And the first one is just 2 pi. So we need to evaluate the second one, okay? For the second one, I will break that into two integrals. This is equal to 0, 3 over square root of 2 r 9 minus r squared dr and minus 0, 3 square root of 2 r squared dr, right? This integral is easy because that is r cubed over 3 evaluated from 0 to 3 over square root of 2, which is 9 over 2 square root of 2. Okay, let's keep in mind this. Let's find the second one right here. For this integral, I put u equal to 9 minus r squared. I find du is negative 2r dr. So r dr is negative du over 2. Okay, and let's find antiderivative of that function, right? Of function right here, and then we plug 0 and 3 over square root of 2 at the end. So I get antiderivative of, I have negative 1/2 right here, okay, square root of u du, and that is negative 1/2 u to 3/2 and divide by 3/2, okay, and this is equal to negative 1/3 u 3/2. At the end, we need to plug the substitution back here. I get negative 1/3 9 minus r squared 3 over 2, right? Now, I will plug integration limit into this function. I have our integral is nothing but negative 1/3. I write here 9 minus 3 over square root of 2 square cube minus square root of 9 minus 0 cube. Alright, so I have negative 1/3. In here, I will have 9 minus 9 over 2 square root, right? And cube. In here, I have 3 cube. So we might simplify this. This is, just 9 over 2 square root. And apply cubic in here. We have 27, right? And negative 1/3. Overall, I will get negative 1/3. In here, I have 27 over 2 square root of 2 minus 27. So this is negative 9 over 2 square root of 2 plus 9. Alright, so we already have results for the first integral. Overall, I will compile this number and this number together, right? is we have, this integral. So basically this integral is equal to negative 9 over 2 square root of 2 plus 9 minus 9 over 2 square root of 2, right? So this term and these terms, they are the same. So I have 9 minus 9 over square root of 2. Agree? All right. So that's what we have for this integral. Okay. Now we multiply that number with 2 pi, we get the answer. So let me multiply this. 2 pi times 9 minus 9 over square root of 2. You get 9 pi and you multiply 2, right? You bring 2 into the parentheses. You get 2 minus square root of 2. And that is the final answer. That is the volume of our solid region. Okay, so you can see, actually, we still can solve this problem using cylindrical coordinates. Make sense? But look at this. It's still pretty long, right? Now, let's apply the formula of triple integrals in spherical coordinates for this problem. So in this situation, your function is just 1. Just 1. Makes sense? Okay, we have to find intervals of integration in terms of phi, theta, and rho. Makes sense? Look at this. If you pick some point in this solid region, you have to measure the angle, right, between this vector and the z axis. Since we have the cone, this angle should not bigger than the angle right here. Makes sense? Because this is the border. Makes sense? All right, that is about, phi. So we need to find the biggest angle in here. And we can see actually phi is between 0 and this guy. Okay. All right, next. How about rho? If this is your point, so that point should be inside the sphere. Rho should not be bigger than the radius of the sphere, right? So you can see rho between 0 and the radius, which is 3. Okay. So how about theta? In order to find theta, you just find orthogonal projection of that point on the xy plane, right? We already figured out that it's just a circle right here. So the theta should go from 0 to 2 pi. Make sense? We already have all intervals of integrations except one point, except this guy. Let's find that out, okay? Because, we already have intersection between the cone and the sphere. So we know the circle right here, right? So based on that, we can find the maximum angle. All right, let's do that. We already seen that, the circle is x squared plus y squared. We already saw that the circle is x squared plus y squared equal to 9 over 2. And z equal to 3 over square root of 2. Makes sense? So I have the following one. Z equal to rho cosine of phi, right? We have that relation. Since that point is on the sphere, rho should be equal to 3. So I have z equal to 3 cosine of phi. Okay? And z is equal to 3 over square root of 2. From here, I can solve for phi, right? I have cosine phi is equal to 1 over square root of 2. So phi is equal to pi over 4. That means phi is in between 0 and pi over 4. Make sense? Look at this. This is pi over 4. All right. Now let's apply the formula right here to find the volume. So since the function f is just 1, we don't have this term, just 1. Okay. We have the volume is equal to, with respect to theta, I have 0 to 2 pi. With respect to phi, I have 0 to pi over 4. About rho, we have 0 to 3 rho square and psi of phi d rho d phi d theta. This integral looks better than the previous one, the one with cylindrical coordinates. And now you see, the function is rho square psi phi, right? We can separate them. So we can rewrite this integral as product of three integrals from 0 to pi d theta times 0 to pi over 4 psi phi d phi, and from 0 to 3 rho square d rho. Okay, so this is 2 pi. This is negative cosine phi evaluated from 0 to pi over 4, right? And this is rho cubed over 3. So evaluated from 0 to 3, that means equal to 9. And in here I have negative cosine of pi over 4 plus cosine of 0. This is 1. This is square root of 2 over 2, right? So I have three numbers, 2 pi, this, and 9. We need to multiply them. We have 2 pi times negative square root of 2 over 2 plus 1 times 9. And the answer is 9 pi 2 minus square root of 2. Let's compare this with the one we just found right here. Right here. You see? But if you compare two solutions, you would think, yes, the solution in spherical coordinates is much easier. All right, so what we have learned in this example? Let's go back to the region of integration. This is a part of the sphere. Look at this. So that's why, in this situation, spherical coordinates work really well, right? In the previous example, the integration region is what? Is cylindrical. So that's why we use cylindrical coordinates. Make sense? So I hope that with these two examples, we learn when we need to use cylindrical, when we need to use rectangular, and when we need to use spherical coordinates. And don't forget, we have formulas for each of them. Make sense? If we use cylindrical coordinates, you just multiply, the function with r right here. Okay, don't forget this. But if you want to use spherical coordinates, you have to multiply with rho square and psi phi. All right? So I hope that, the video is clear enough. But if you have any questions, just feel free to let me know. Thank you.